VinFuture Prize, a new global science and technology prize for humanity from Vietnam. One VinFuture Grand Prize of $3 million. 3 additional special VinFuture prizes valued at $500,000 each. VinFuture Prize honors science and technology work that creates or has a high potential to create meaningful change in the everyday lives of millions of people. Join us to make a change for a better future.
Ladies and gentlemen, welcome to the August InnovaTalk webinar presented to you by the VinFuture Foundation. I'm Vi Dương, and it's my pleasure to be your moderator. Today is on the exciting world of batteries and fast charging technology. We'll explore recent advancements and their potential to significantly impact sectors such as automotive and energy. To get things started, let's meet our esteemed panelists for today. First, we welcome the return of Professor Rachid Yazami, 2023 VinFuture Grand Prize Laureate, Founding Director and CTO of KVI Holdings.
Okay.
As a pioneer in battery technology innovations, Professor Yazami will be the chair of today's webinar. We are also honored to have Professor Xuejie Huang, a leading figure in battery research, to join us as our distinguished speaker. He is currently a professor at the Institute of Physics, Chinese Academy of Science, the deputy director at the Songshan Lake Material Laboratory, and the editor-in-chief of Energy Storage Science and Technology. And last but not least, our special guest for today's webinar, Mr. Duong Quang Tien, Chief Battery Engineer at U.S. Department of Energy, currently managing the Advanced Battery Material Research Program and the Battery 500 Consortium at Vehicle Technology Office. To set the scene for our conversations, let's watch a brief introduction trailer that provides an overview of what we'll be discussing today.
The future of energy storage and electric vehicles hinges on breakthroughs in battery and fast charging technology. Scientists and engineers worldwide are racing to develop batteries with higher energy density, longer lifespans, and improved safety. The push for faster charging capabilities is also intensifying. This August, the InnovaTalk webinar will delve into the latest advancements in battery and fast charging technology, exploring how these breakthroughs will revolutionize industries from automotive to energy storage. For this topic, we welcome the return of Professor Rachid Yazami, the 2023 VinFuture Grand Prize Laureate and a pioneer in battery technology, as the chair of the webinar. Professor Yazami, currently serving as founding director and CTO of KVI Holdings, has been a driving force in battery technology innovation for decades. He pioneered the exploration of reversible electrochemical intercalation of lithium ions into graphite, laying the foundation for the development of modern lithium-ion batteries. Moreover, his work has also brought extensive insights into the thermodynamics of battery charging and discharging processes, which was described in the fundamental Yazami's battery theorem. Joining him on the panel is the distinguished speaker, Professor Xuejie Huang. He is currently a professor at the Institute of Physics, Chinese Academy of Sciences. His contributions to the advancement of battery technology are immeasurable. He has developed technologies for materials, batteries, and machines for the lithium-ion battery industry in China. In 1998, he founded Felion Battery Company Ltd., which is now a leading producer of lithium-ion batteries for light electric vehicles in the world. And last but not least, we welcome a very special guest, Mr. Duong Quang Tien, a leading energy specialist, to join the InnovaTalk webinar. Mr. Duong has been an integral part of the energy storage R&D effort within the Vehicle Technologies Office VTO since 1994. As the Chief Battery Engineer at the U.S. Department of Energy, managing the Advanced Battery Materials Research BMR program and the Battery 500 Consortium at VTO, Mr. Duong Quang Tien brings a wealth of knowledge and experience to the webinar. Don't miss the opportunity to learn from our esteemed speaker, whose invaluable insights into the development of fast charging technologies will undoubtedly enrich your understanding of the field.
Without any further delay, I present to you Professor Rachid Yazami, the esteemed chair of our discussions today. As 2023 VinFuture Grand Prize Laureate and the founding director and CTO of KVI Holdings, Professor Yazami insights are highly anticipated. Please join me in welcoming him to the stage.
Hello, good morning and good evening to Mr. Quang Tien in Washington, D.C. I'm very, very honored to share this webinar for InnovaTalk of the VinFuture Foundation. Today, we have a very hot topic, which is relating to lithium-ion batteries and also to their applications in the electric mobility in general, which is the future. And I will present a very short overview of the current situation of the of the batteries and also the innovations that are behind the fast charging. My colleague and friend, Professor Xuejie Huang, unfortunately for some technical reason could not connect to this webinar, but fortunately he sent me his slides, and I will try to use his slide and comment a little bit about what I understand from his presentation after my talk. Okay, so let me first share the screen with you. Just an introduction. I would like just to show you where we are now with the evolution of the lithium-ion battery market. So it's expected that in 2030, we will reach the 4.7 terawatt hours, which is 10 powers 12 watt hours. And the production of lithium-ion batteries is increasing very, very fast. It's 27% every year. And the market will be close to $470 billion in 2030. And most of it you can see from the right side that mobility is the major application of the lithium-ion batteries, which actually illustrated in this slide. So you can see here that in 2030, on the right side of the slide, that we will be reaching 3.7 terawatt hours in 2030 of batteries. And this sector is the most dynamic, the most promising for the industry, and it's driving a lot of excitement in the industry and also, of course, in academic work to improve the performance of batteries. So what can be recognized as the current limitations where activity should be focused on regarding lithium batteries? Number one is safety. We have to make batteries safer, that's for sure, because otherwise the end user of electric vehicles may have a fear that the battery can catch fire. So we have to do a lot in the safety sector. And unfortunately, this sector doesn't attract enough attention, but it's crucial. The other one is the long charging time. People want to charge their batteries in less than 10 minutes, which is almost the same time that we use to fill our tank in internal combustion car with gasoline. So 10 minutes should be great. And with these 10 minutes, we want to have a very long driving range. So the driving range should be extended from current about 170 to 600 kilometers to about 900 kilometers. And also we have to extend the life of the batteries so we can use them for over 250,000 kilometers, which is about the average today. So what we don't want to see is this kind of images. This is a car that has unfortunately caught fire. Fire due to overheating of lithium-ion batteries can be observed and reported in many, many devices that use lithium-ion batteries. So safety is something that is crucial for the future of lithium-ion batteries. And we have been working on this, and I would be happy maybe in another occasion to tell you what we have been doing using thermodynamics, entropy measurements to deal with the safety of batteries. But today, the topic is mostly about fast charging. So fast charging is using, batteries now are charged using mostly constant current based technologies or methods. And constant current is like a CCCV, constant current, constant voltage, or MSCC, which is the multi-stage current, constant current. These technologies are not able to fast charge batteries because of heat generation. Forget about charging a battery from 0 to 100% in 10 minutes using a constant current. The battery will heat up and there is a risk of thermal runaway. Instead, we developed recently a new method based on so-called nonlinear voltammetry, NLV, which I would like to illustrate here very fast, very rapidly. So in the NLV, what we do is instead of controlling the current, we control the voltage. And we apply a series of voltage plateaus. Within each plateau, the currents go to zero. So this is what we call a rest. And so the red color curve here is the voltage profile, and the blue color is the current profile. And this is an illustration of fast charging in 20 minutes for fully charge a battery in 20 minutes, which means that if we go from, say, 20 to 80% state of charge, it will be only 12 minutes. Okay, so you can see actually that the red curve, there is a bottom voltage, which we call pseudo open circuit voltage. This is when the currents go to zero. The other point is that the current is never constant. So in this NLV, we apply constant voltage and the current is never constant. So just to illustrate this, we tested NLV on commercial batteries that are used in many devices, including power tools. And we were able to charge this battery in 10 minutes, as you can see on the left-hand side with the same, the voltage is in red and the current is in blue color. On the right-hand slide, we have the temperature evolution during the charging in 10 minutes. And you can see that we are below 50 degrees C. All right. The temperature is very important for safety and also for the life of the battery. So we think that this technology will be applied in the future for electric cars and will hopefully be implemented for the next decades. All right. So this is the end of my introduction for this very hot topic that is fast charging technologies. And I don't know if in the meantime, Prof. Xuejie Huang was able to join us. If not, yes. I can. Yeah, you are here.
Yes, I'm here.
Okay.
Yeah.
Okay. Very good. Very good news. So okay, I leave the screen to you.
Okay. So it's my great honor to be here to present the new materials to upgrade the EV batteries. You know, I will give very short, brief introduction about the cathode materials and the EV batteries. Nowadays, the most popular batteries are LFP batteries. But of course, we also have NCM or NCA batteries for premium EVs. But for the next generation, we will expect to have even higher energy density battery for the premium EV and also mainly for the, plane. And also we need high energy density economical type electric vehicle battery. Okay. So firstly, we have developed a very dense high nickel ternary oxide cathode material for the EV battery applications. We need to increase the content of nickel and decrease the content of cobalt to get a high capacity but lower cost but the problem is the safety, the stability of this material. And then we decide to change the philosophy. We try to change the percent polycrystalline NCM 90 or 95 to very dense polycrystalline particles. For to make it, we need to mix different elements, very small amount, but very effective to decrease the first particle grain, and then we can get very dense and very strong secondary particles for applications. And then we can see, compare with the commercial material, we got very dense, cathode material with very high content of nickel. By using of this material, we can get very high capacity. For example, this cell can be sold at 200 milliampere hours per gram when we use this material for the EV battery applications. Now, another important thing is the safety. In this case, we can stabilize the oxygen. It means during heat generation, when the temperature of the cells is increased, we can, reduce, the content of the oxygen evolution, and also we can reduce the temperature for the oxygen starting to evolve from the material. It's very important for the safety. Another important thing is the strength. For the high energy density cells.
In the meantime, I would like to introduce our special guest speakers for today's webinar, Mr. Duong Quang Tien. Mr. Duong has been an integral part of the energy storage R&D effort within the Vehicle Technologies Office since 1994. As the Chief Battery Engineer at the U.S. Department of Energy, managing the Advanced Batteries Material Research Program and the Battery 500 Consortium at VTO, Mr. Duong Quang Tien brings a wealth of knowledge and experience to the webinar. So let's welcome Mr. Duong to the virtual stage.
Okay. Thank you for having me. A good evening, and I guess good morning in Vietnam, in Singapore, and in Beijing. So I would like to, very honored to share the work that we have supported at the Office of Vehicle Technology, U.S. Department of Energy. So today we talk about the fast charge. So in general, the typical charging protocol is a constant current and then a constant voltage. Basically, when you hit the upper voltage limit, you begin to do a constant voltage charging. So you look at the chart here, the plot here, especially the top plot. So what we try to do is take 3 cells, they're all identical cells, and try to figure out how much charge you can charge them up in 15 minutes at different rates. So typically a C rate means an hour, 2C rate means half an hour of charging, and so on. So you can see here, the higher fast charge rate does not translate into more return energies if it is outside the cell's capability. So the plot clearly say that, for a 2C rate, you get almost half of the energy back compared to a 3.2C rate and a 4C rate. So that's what it means in the top charge. The second plot on the bottom, I try to show you the effect of fast charge relevant to cycle life. And you can see clearly there are 3 plots, one with no fast charge, one with 25% fast charge, one with 100% fast charge at room temperatures. And you can see the frequent use of fast charge results in shorter cycle life. Very clear. Now, you may ask yourself what limits fast charge and how do these issues impact cell performance? So on the left-hand side, one of the reasons is lithium plating. And you can see that as a loading increase from 2.2 to 3.3 to 4.4 milliamp hour per centimeter square. In other words, when you build an electrode thicker and thicker, you result in more lithium plating. As more lithium platings, it reduces electrolytes, causing the formation of new SEI that will tie up lithium ions, and eventually you have more capacity loss. And again, the second thing that can happen is temperature rise. At faster charge, at 4C and 3C and 2C, you can see the temperature rise, accordingly. And one good thing about high temperature rise is the high temperature rise can improve electrokinetics. It also may reduce the overall lifespan of the cell because it accelerates degradation of electrolytes. And the third thing we like to talk about is the potential, would be rare, but it's potential cathode particle breakup. Elevated rates can promote cathode cracking. Electrical isolation results in loss of active material and transmission metal dissolution. So those are the limits of fast charge. Now, this slide tells you clearly through X-ray synchrotron, most of the lithium plating is at the end, at the separate side. You can see clearly the yellow area, that's where the lithium plating. So one of the goals that you want to do fast charge, to enable fast charge, is to require reaction to occur more uniformly in the graphite, not plating lithium at the area of the separator and the graphite. So how do we do this? We do this in a program by doing mathematical models, So this plot show you a lot of interesting things. The top of the table is a cell built at 4 milliamp hour per centimeter square, and basically a typical loading for EV batteries. So with this kind of loading, normally you will get 230 watt-hour per kilogram at C/3 rate. But look, if you fast charge them at the 6C rate or the 4C rate, and you watch the lithium plating, you can see on the top, the baseline is for 6C and 4C, and look at the bottom, it's only like about 20 or 30 watt-hour per kilogram. See that? The next row you do is you model with reduced tortuosity. You can see you can get more specific energy. The next row is you perform the fast charge at 45 degrees C. You can see it getting better. And at 60 degrees C, it's getting better. And then you do a 45C with reduced tortuosity, it gets even better. And 60 degrees C plus reduced tortuosity, it gets even better. And so on and so on. And finally, with a new generation of electrolyte, it gets the most of the specific energy, almost to 180 to 160 watt-hour per kilogram, depends on what rates you want to charge. So some of the noting here is you can see the 4C fast charge rates, raising temperatures had the maximum effect. So that's one point you want to take into account. However, higher temperatures accelerate degradation mode. Another point we would like to make is reduced torque velocity facilitate fast charge. So to facilitate fast charge, we need a combination of solutions. And that's what we discussed in the next slide. The first thing you want to do is to reduce torque velocity. So you can do that by two different processes. The first process on the left-hand side is to have a dual layer anode. So what you do is you have a layer of electrode with larger particle, larger porosity inside, and you coat another layer of electrode with a larger, the smaller particle inside and larger particle outside. By doing that, you facilitate much faster lithium intercalation into graphite. Another way to do it is to do laser ablated anode. Basically, you burn the surface electrode and you can make holes in the electrode to increase the porosity. So that's one of the solutions. The second solution here, you can see on the right-hand side, you can develop improved electrolyte with higher ionic conductivity and transfer number to allow faster lithium-ion transport. So this plot shows you what happens after you do 60 charge to a single cell at different electrolyte. We call Gen 2, electrolyte 1, electrolyte 2, and electrolyte 3. And after that, you do a 1C discharge capacity to measure the capacity of the cell at the 1C rate. And you can see the one with 2-time ionic conductivity and 0.15 increase in transfer number has the most specific capacity. So that tells you improved electrolyte can allow much faster charge. So you can see that a rational design approach has led to significant advance in the fast charge. By applying to those processes I described on the previous slide, we have demonstrated a 10-minute charge at 4 milliamp hour per centimeter square, a 15-minute charge at 4.8 milliamp hour per centimeter square. So you can achieve several forefront innovations to design by new electrode architectures using dual layers and laser ablations. You use multiple electrolyte compositions with improved transport. You can develop multiple lithium detection methods to quantify heat generations during fast charge and impact on life, and method to detect SOC and lithium plating across all scales. So in summary, the optimum time to fast charge of current lithium-ion batteries is about 30 minutes or so, roughly about 2C rate. Charging battery faster than 30 minutes at 3, at 4, at 5C rates, we consider that as extreme fast charge. It can be, it's possible with new electrode designs and improved electrolyte. New cell design can be expensive. Long-term impacts on cell performance and cycle life are still being studied. Most EV batteries are not yet ready for extreme fast charge. Battery warranty may be voided. And finally, availability of utility infrastructures to provide power for extreme fast charge is a limiting factor. So those are the conclusions.
we will turn to the panel reflection. I believe that Professor Xuejie Huang can join us in this section. So to wrap up our discussions, I would like to invite all our panelists back to the stage for brief panel reflections. This will be a 5-minute dedicated for all panelists to share any concluding remarks before we turn into the highly anticipated Q&A sessions. Please join me on the stage.
Yes, okay. Thank you so much. Sure. Yeah, actually, my feeling is that what Mr. Duong presented is very interesting. I think this is really interesting to have this approach that is more relating to the architecture of the battery and the way how the anode and cathode are designed to avoid the overheating and also lithium plating and hopefully get a battery that is safe and also long life. So this is very interesting. This is one very important approach that is relating actually to the design and the engineering of the cells. However, I still, as a scientist, I think it's time for the lithium-ion battery community to think about other approaches for charging batteries rather than those based on constant current. Constant current has been historically the main method for charging batteries for over 150 years, since the inception of lead-acid batteries until now. For lithium-ion batteries, there are some variants, like based on constant current, constant voltage, or multi-stage current, and then etc. So it's okay. The thing is that we have to keep in mind that a battery is an electrochemical device, and electrochemistry as a science is a non-linear. And when we apply a constant current, it's like we apply a linear signal to a non-linear system. So there is a limit, and the limit is only when we want to charge very fast. And so as long as we have like more than 1 hour to charge a battery, constant current methods apply very well. And I think it should not put any problem because it's already there. We charge our cell phones and we charge also our power tools and many devices containing lithium-ion batteries in 1 hour, about 1 hour. Okay. Now we go to the below 30 minutes, which is recommended by Mr. Duong and the Department of Energy, which I fully agree that we have to go below 30 minutes, if not below 20 or 15 or even 10 minutes. Of course, as we shorten the charging time, we put the battery under stress. Yeah. So there are different ways actually to cope with this. Number one is we never go to zero state of charge when we are using a mobile device. Otherwise, we have to push the car or the two-wheelers. So usually the system will send like a notice or something to the driver, to the user, that they have to go to charge the battery when the state of charge reached 20%. Okay, so that's number one. So we can, if we start from 20%, and then we avoid to go to 100%, because between 80, 85, or 90 to 100%, this is where the battery is also another stress on the battery, and the temperature will tend to go higher at the end of the charging process. So basically, for electric mobility, what is recommended now is to charge a battery from an initial state of charge, which is not zero, and the final state of charge, which is not 100%. By doing this, we can extend the life, as Mr. Duong showed, actually, for the satellites. We can have 25% only a range of the state of charge. We have many thousands of cycles. It's not a problem. So again, it's always a trade-off between the charging time and also the life of the battery and the safety of the battery that we have to find. And this is something that can be done, of course, by improving the battery materials and battery engineering and design and so on, but also by the battery management system. And the battery management system what I actually somehow advocate these times is that we have to learn from the artificial intelligence, sector, which is booming now. And we can collect a lot of data on the battery in the process of charging and the process of using the battery during discharge. And if we collect all this data and process them in a very smart way using artificial intelligence, I'm sure we can solve many of the current problems that are, as I mentioned, the safety, the fast charging, the range, the driving range, and also for the lifespan of the battery. So these are all many direction of R&D or research for academia and for industry that I see in the future. And hopefully, because of, as I showed in the first slide, we are going to reach 4.7 terawatt hours of batteries, which means that we are going to produce over 40 billion cells every year by 2030. So we have to consider all these aspects like safety and others, performance of the battery that need to still to be improved. And I'm certain that there are many brains all over the world working on these areas. And of course, Prof. Xuejie Huang started to show us, his approach from the cathode perspective. And maybe you can come back, Xuejie, and tell us a little bit about what are the conclusion of your finding, okay? Because now we have you again. Hello.
Okay, thank you. Yeah. So it's my pleasure to back again. For the materials developing, we want to improve the performance and decrease the cost for the cathode materials. Presently, for LFP batteries, it's very popular. We need again to increase the cycling life. Not only for the energy storage, but also for electric vehicles. We need to have very high energy density and also very high, economical, feasibility. So then we need to reduce the cost. And the best way is to increase the cycling life. For the NCM battery, we need to continue to increase the safety of the cells. As you know, in some cases, if the content of liquid is too high, of course, we will make some problem. To overtake this problem, people need to introduce some solid state electrolyte to the cells. So I think we are continue working on materials and also battery technologies to improve the safety of the NCM battery. For the future, I think we will have the third generation batteries. It means silicon-based anode will be widely used in the anode. Also, we will expect a fast charging battery. As Mr. Tien mentioned, for the charging.
The goal of the U.S. Department of Energy is to charge, to return 60% of charge in 15 minutes. And typically we start at 20% and charge it up to 80%. Believe it or not, in real life, the last 20% may take the same amount of time to go from 20% to 80% of charge. But the reality is none of the lithium-ion battery can do that, in 15 minutes. So our approach is more like a very total approach. We look at the electrode designs, modification. As like Rachid pointed out, we also look at charging algorithm also, but that's not the main focus of the program at this point in time. Mainly on the electrode designs, things like that, and changing the tortuosity of the electrode, 2 layers of electrode material, one with smaller particle inside and another layer with larger particle outside, ablations of electrode to remove, to burn some of the electrode material away to increase the tortuosity, and to design very high improved electrolytes and things like that. And all of that together with, charging at high temperature and things like that would allow and facilitate fast charge. But certainly we will look at your nonlinear volumetry to understand a little bit more about that and maybe deploying it in our program. But at this point in time, we mainly focus on electrode designs at this point in time. But as I said, we can do it. The problem is new cell designs, new electrode designs can be expensive. So that's the drawback of everything we do. We demonstrated we can do it, but to redesign the electrodes in the cell can be expensive at this point in time.
Thank you all panelists for really insightful sharings. So we will, from our side, we would also like to share an important announcement. The VinFuture Foundation is now calling nominations for the 2025 VinFuture Grand Prize and 3 special prizes. The nomination portal will be open until April 17, 2025. We hope to see you joining us in making a positive impact on humanity by nominating deserving technological innovations that have improved people's life.
Greetings from the VinFuture Prize. Please find instructions for the nominator following these steps. To begin, you can access the nomination portal at online.vinfutureprize.org/nomination. Or you can scan the QR code you see on the screen right now to open the nomination webpage. On this webpage, you can download the instructions and the endorsement letter template. In the instructions, you will find the complete nomination form, where you can draft the nomination whenever you have time. Then, you can copy and paste the draft into the online portal. Please click on Sign Up, and upon successful registration, you can simply use your ID and password to log in. After login, please click Nominate Now to start a new nomination form. Subsequently, you can see 7 content tabs on the nomination form. To begin the nomination process, on the first tab, please select the prize category as well as the type of nominee, whether it is an individual nominee or a group of nominees. Then click the Start button to proceed to the second tab. And we would like to call your attention to tab number 5 and tab number 7. On tab number 5, your evaluation, you're invited to give your evaluation of the nominee's invention, including its groundbreaking discovery, scientific fundamental knowledge, specific approach, uniqueness, and advancement. Then you are required to clarify if the invention can be transferred to a product and highlight its most significant socioeconomic impacts. This includes the number of beneficiaries, such as people, countries, and continents. Additionally, please explain how you believe this invention has or will potentially transform the everyday lives of millions, if not billions, of people. Next, please provide information on the history of the invention, such as when and how it started, and who else, except the nominee or nominees, was involved in initiating or contributing to the invention. About tab number 7, supporting documentation and evidence. There are several important documents that the nomination portal and form require, and we would like to call your attention to 3 critical items. The first one is the CV of your nominee or the CVs of your group of nominees if you are nominating a group of people. The second important item is the endorsement letter. 3 endorsement letters or more are strongly encouraged, but 1 is mandatory. The third one is the additional form of nominees. Please be as specific as possible when providing the information. Additionally, you are strongly encouraged to include any valid intellectual properties, publications, patents, or other supporting documents that provide evidence for the nomination. Finally, after filling out and providing all the content in the 7 tabs, please click on the Submit button at the bottom of the page to submit your nomination. If you have any questions or you face any technical issues, please email us at secretariat@vinfutureprize.org. We will be more than happy to assist you in your nomination process. Thank you very much.
And now, the moment you have all been waiting for, the Q&A sessions. Feel free to actively participate by using the raise hand function. We will unmute you for direct exchange with our panelists. For those who prefer a more indirect approach, you can simply type down your question in the chat box, and we'll make sure that your question reach the most relevant panelists within our time frame. Okay, so it seems like we have the first questions. Can I invite Mr. Hieu-Minh Chen from Hanoi University of Science and Technology to unmute and directly discuss with our panelists? Mr. Hieu-Minh Chen, please.
Hello, can you hear me?
Yes, we can hear you now.
Okay, thank you very much for your presentation today. My question is...
Excuse me, can you turn on your camera, please?
Sorry, I'm not stay in a convenient place to turn on the camera, so I would like to...
Okay, that will be fine. Thank you.
Okay. Okay, so my question is about Professor Yazami mentioned about the ranks of the charge for the battery to maximize the battery's life is about between above 0 to about 85%. So what is the physics behind such a succession?
Okay.
And if we follow such succession, how many percentage of the battery life we can increase compared to the normal charging from 0 to 100%? Thank you.
Okay, thank you for your question. Actually, when you charge a battery, basically what you do, you are transferring lithium ions from the cathode to the anode. So you are delithiating the cathode. So the amount of lithium in the cathode is getting lower and lower. And then you are storing your lithium through the electrolyte into the graphite anode, basically, or silicon-based anode. Okay. These processes are controlled by thermodynamics of electrodes and also by the kinetics of electrodes. And what we found is that graphite has to expand a little bit at the beginning of the lithium intercalation. So graphite, the interlayer spacing is about 3.35 angstroms, and it has to expand about 10% to go to 3.71 angstrom after lithium intercalation. This process is kinetically activated in the sense that the graphite is a little bit resilient to do this expansion. And so for the first state of charge of the battery, say between 0 and 10%, there is a resilience of graphite to store lithium. So kinetically, it means there is an overpotential at the anode side that somehow slows the kinetics of lithium intercalation into graphite. Okay, so this is why also when you look at the internal resistance of a cell versus state of charge, at the beginning, you can see that actually the internal resistance is quite high, and it drops at the state of charge increases. And it's almost constant for between, say, 20% and 80%, and then it tends to increase again. This is a general trend. I mean, of course, case by case, it may be different. So the reason why it is recommended to use only part state of charge between for charging the battery between, say, 10 to 90 or 20 to 80% is because of this, because we don't want to have any limitations in the kinetics of anode and cathode during the charge of the battery. Otherwise, if we have an overpotential, that translates into the battery temperature increasing. Okay, so that's why we are recommending this, and also because practical things is that when you have an electric vehicle, you don't want to go to 0% state of charge.
Oh, thank you. And my second question was that how many percentage can we lengthen the battery life if we follow such instruction?
So you are talking about the effect of the state of charge during charging versus the life of the battery. Is that correct?
Yes, that's correct.
Okay. So actually, the people from NASA can answer better my question because they have satellite that have rechargeable batteries, and they know that actually when they charge the battery only part time, part state of charge, say between just maybe 20% total, changing the state of charge, they can afford many 10,000s of cycles. Okay. So in general, there is an exponential function between the range, the state of charge range during charge, and the cycle life. Okay. So of course, if the state of charge range is zero, the life is infinite. But this is just a joke. But if you go to 10%, 15%, 20%, you see that actually you are dropping from maybe 20,000 cycles to 2,000, 5,000, 2,000 cycles, and then maybe around 1,500 cycles for generally when you are using 20 to 80%. But of course, this depends on the materials that you are using, the battery design, and also of course the chemistry, the electrolytes, and so on. So this is just a general view that if you reduce the range of state of charge, you increase the life of the battery exponentially.
Yeah, thank you very much for your useful information.
Thank you very much, Professor. So now we have the next live questions from Mr. Nguyễn Hữu Đăng from Battery Research and Development Institute from VinFast. Mr. Đăng, can you please unmute yourself and turn on your camera and discuss with our panelists?
Anyway, we are looking for the very high energy density material, and I'm very impressed by the presentation of Professor Xuejie Huang. Although we cannot fully hear your presentation or fully see your results, but I have some questions about your NMC90. So you show that the cycle life of NMC90 is at 1C1C, the charge and discharge rate is about 90% at 500 cycles. So how about the fast charge ability of your material? And the second question is your material in the lab scale? I wonder, can it be in the near future in the mass production scale? Because we are from the material team and we are looking for some very high energy density material. Yeah, thank you.
Okay, thank you. We have not only a laboratory to make them research, but we also have pilot factories in Sunshine Lake laboratory. So we can produce up to few hundreds kilograms materials per batch. So if you like, you can get our samples. For the nickel 90 and also for the nickel 94 samples, you can test the performance, and also you are welcome to contact us. We have a laboratory not too far from Hong Kong. We can make not only an NCM, but also we make good anode materials based on silicon and tin. We can also provide samples if you like.
Yeah, thank you for your answer. And how about the fast charge ability of your material? Because we are talking about the fast charge ability of the battery, right? How about your thought on your material on the fast charging?
Yes, for the fast charging, I would say for the cathode material, you do not worry too much about that, because we use a small amount of niobium into the material, and it helps to improve the rate capability. So I would say the fast charging capability for the nickel 90 is very good. As for the anode material, you need to use good material, also a very good battery design. I think we can discuss. But anyway, for the nickel 90, you can use it for fast charging battery.
Yeah, thank you. Maybe I will reach out to you after this meeting. Thank you very much.
Okay, thank you.
Thank you, Professor Xuejie Huang. And now we have the questions to Mr. Duong Quang Tien from Dr. Xuejie Huang from Chungnam National University, South Korea. Mr. Duong Quang Tien, can you tell me how do you test constant voltage mode for fast charge conditions, and how do you reduce time for CV mode under fast charge conditions?
So certainly, for us, a constant voltage charging is very risky. We don't recommend doing that. But in principle, you can emulate a constant voltage charging by doing pulse current. You know, you do a high pulse and you reduce the current. You do a pulse and you reduce current. So when you pulse the current, you get to a voltage close to your upper voltage limit, and you reduce the current. So by doing so, you kind of emulate a constant voltage charging, but we would not recommend that. Do I answer your question? You can do that. Yeah. And regarding the constant voltage, so what you do is the best way to optimize your constant current to a point to get more energy to the battery cell as much as possible, without reaching the upper voltage limit. When you are at the upper voltage limit, you basically clamp the voltage of the battery at that point in time and reduce the current gradually until the current go down to about 1 amp, something like that. So that's the end of the charging.
Thank you, Mr. Duong Quang Tien. And next, we have another questions for Professor Xuejie Huang from the audience. Professor Huang, what are the best cathode material for the fast-charging lithium-ion batteries? Can you please tell me?
Okay, it depends on the applications. You know, not only for the LFP, but also for the NCM batteries, you can charge it quickly once you have a well-designed anode. So I would say for fast charging, it's very much dependent on the anode, not on the cathode. But anyway, the cathode must be fit to the fast charging. So in my opinion, for the EV applications, for different material, different chemistry, LFP and also NCM, you can develop a fast charging type battery for the required applications.
Thank you, Professor Xuejie Huang. We have another questions from Dr. Xuejie Huang to Professor Rachid Yazami. What about the lithium plating or lithium dendrite growth when NLV is applied?
I think when I presented, I showed that actually we are applying a constant voltage for very, very short time. And then there is a rest for where the currents go to zero for about maybe 2 seconds to 6 seconds maximum. Okay, so we have tested tens of batteries, different batteries coming from all over. We charged them, all these batteries, we were able to charge them below 1 hour. Okay, and we have been cycling them for many hundreds of cycles. We have never observed any sign of lithium plating. Okay, so there is a physics behind. Actually, if there is a lithium that is plating on the anode side, probably during this rest time where the currents go to zero, graphite will absorb that lithium on the surface. That's what our hypothesis, but I have no evidence of it. And I'm working with a group in California Institute of Technology that will model the what happens on the anode side versus the state of charge. If we have some lithium metal on the surface of graphite, what happens? Okay. So because, of course, there is a driving force that will push lithium metal to intercalate into graphite. That's thermodynamically what is expected to happen. But the kinetics of that, is it like 2 seconds or 5 seconds? Is it enough to absorb the lithium metal if there is any lithium plating on the anode side? We don't know yet. But what we observe is that there is no evidence at all of any lithium plating when we use NLV. So that's the exciting part of this NLV technology. The other thing, the merit of the NLV is that we don't need to do the so-called cell balancing, which means that if we have a battery pack with many cells and we have measured the voltages of each cell individually, and during the process of NLV, we could follow the voltage of each cell independently. And we found that actually the difference between cells are below 10 millivolt. Okay, so it means that there is no need actually for cell balancing. We have performed over 1,300 cycles, charge and discharge cycles, full charge from 0 to 100% in 25 minutes. And we have never, we never needed actually to do any cell balancing after full charge. Okay, so this is the two merits that we have, at least the merits that the NLV is bringing. But of course, I mean, we have to go to the physics behind the anode and cathode degradation. Basically, the anode degradation comes from the SEI, the solid electrolyte interface that is growing and makes the anode more and more resistive. On the other side, from the cathode side, what you have is this what's called cation mixing, which means that the lithium ions will go to the metal layer and the transition metal will go to the lithium layer. This is the cation mixing. And from first principle calculations, it have been proven that actually this cation mixing takes some time because lithium has to move from the octahedral side to the tetrahedral side in the lithium layer, go to the tetrahedral side in the metal layer, and then go to the octahedral side in the metal layer. And this process takes more than seconds. So what does it mean? If I apply a little bit higher voltages, of course, maybe lithium will go to the tetrahedral side in the lithium layer, but I'm not allowing it enough time to go to the other layer. And so it goes back to the fundamental state, which is lithium goes back naturally to the octahedral side. By doing this, we avoid or we reduce the lithium cation, mixing, or the cation mixing in the cathode side, and we reduce the degradation of the cathode, and we can extend the life of the battery, although we are a little bit higher in voltage than what is recommended by the battery manufacturer, because the battery manufacturer, if they are using CCCV and you are applying a CV for a long time, yes, if you are above 4.2 volt or 4.3 volt, you will degrade your material because you are applying the CV for over 10 seconds or 20 seconds and so on, and then you have a degradation. Okay, so this is just to tell you, we don't see lithium plating using NLV. We don't need to have cell balancing. And also, we are not degrading much the cathode material. It degrades, of course. We are losing capacity. But after 1,300 plus cycles, the capacity loss is less than 10%.
Although we have a lot of questions, but since we are on a time limit, so I would like to invite Professor Xuejie Huang from Pennsylvania State University to ask one last question to our panelists. Please, Professor Huang, can you unmute yourself and turn on your camera?
Yes, I turn on my camera, and can you hear me?
Yes, we can hear you now.
Okay. Yeah, I have a question to Professor Yazami. So for the fast charge, what you mentioned, just to change the protocol and to enable this fast charge. What I heard is really amazing. But at the end, so this just changing the protocol to enable the battery to achieve this fast charge capability and also high energy density is challenge. I'm a little bit skeptical about your statement. So without showing the data that you did not observe this lithium plating will be difficult to accept this one. So not just the material level for lithium ion absorbed on the graphite, but at the electrode level. So when you have high energy density lithium ion, for example, 250 watt-hour per kilogram, you need to have a certain thickness. So it's not just the transport at the surface or absorption of the surface. It's also about this kinetic over across very thick electrode. So as Mr. Tien presented the work that the lithium plating happens on the top electrode. So there are so many papers, the fast charge, thousand or million cycle, like supercapacitors. You can make a tiny thin electrode, you can make a fast charge. But if you make a thick electrode to achieve the high energy density, well, the fast charge, that's the issue that the community are facing. So it's very challenging. So I think without the data to show that you characterize the electrode without observing the lithium plating, I think it will be difficult to be, the convinced.
Professor Huang, excuse me. It seems like there is some technical problems with your microphone. So can you check that once again and repeat the questions to Professor Yazami?
No. Sorry, I fully listened to his question, and yeah. I'm able to reply. No problem. There is no technical problem.
The short question is that so the achieving high energy density while achieving fast charge capability is a challenge. Keep the constant voltage at a short period of time is a pretty novel approach. To do that, but I think the intrinsically to solve this fast charge, achieving both of the high performance in high energy density and the fast charge capability is challenging. So as far I know, I have not seen the real data. So especially for the high energy density cell. So that's my question: that do you have any data to show that achieving certain energy density to achieve this fast charge capability, and then explain your statement?
So okay, very good. Yeah, thank you very much for the question. It's very relevant. Actually, just to give you an example, we have received three 21700 cells from the same manufacturer in Korea, Samsung. Okay, this is very public. I mean, they have the 30T cell, the 40T cell, and the 50E cells. Okay, 30T cells is 3000 milliampere hours. 40T is 4000 milliampere hours, and 50E is 5000 milliampere hours. But the form factor is the same. It's 21700.
What is energy density? That's the capacity.
Of course, the capacity, the energy density is somehow proportional to the capacity. So you go from 3 to 4 to 5 proportionally. The same form factor, you have an energy density that is increasing, definitely. Because the chemistry inside is almost the same, but you are right. When you design a high energy density battery, you need to use a thicker electrode, thicker anode, thicker cathode. Okay. So now what we observe is that we put the limits of the NLV. What limits the NLV is the temperature. So if we put like the safety temperature at 50 degrees C, and we start to charge these batteries, the 30, 40, and 50 batteries in 1 hour, and in 40 minutes, and then in 30 minutes, and et cetera, we see what is the fastest charging time according to the energy density of the battery, the capacity of the battery. So we found that of course, this is charging from 0 to 100%. We found that actually, yes, in the 50 E battery, we cannot charge it below 40 minutes because of the energy density is high and because the thickness of the electrodes is larger. So there is a heat generation because there is a higher internal resistance. And then when we go to the 40T cell, which is 4,000 milliampere hour, we can go to 30 minutes. And the good surprise is the 30T cell. This is the one I showed actually in my slide. We were able to charge it in 10 minutes. Okay. So yes, there is a correlation between the energy density and the charging time. Definitely. If we put a limit as the temperature, because I didn't want to generate any heat or overheating of the battery. So I stopped the charging when the temperature reached 50 degrees C. Okay, so this is maybe one part of the answer to your question, and you are absolutely right. The design and also the chemistry of the battery plays a role in the fast charging. Now, what I can tell you for sure is that this NLV method, we call it natural charging. Why is it natural charging? I take a battery is like an athlete, okay? So an athlete, we ask an athlete to run from A to B, all right, in a limited time. Say, for instance, 10 kilometers in maybe 30 minutes, something like that, okay? So the speed, average speed will be like 20 kilometers per hour, which a normal athlete can do. Now, if the road, the path is flat, yes, you can run at constant speed. There's not a problem. However, this is very important to understand that the battery has the thermodynamics and kinetics, and the diffusion coefficient in lithium in anode and cathode is changing with the state of charge of the battery and also with the temperature. So we have to adjust the speed according to the resilience of the battery to take a charge. So you are running and you are going uphill. You cannot run at 20 kilometers per hour. When you are going downhills, you can run at 30 kilometers per hour. At the end, you have a average speed of 20 kilometers per hour. It's possible, okay? So that's why we call it natural charging, because we cannot apply a constant current to a battery if it means that we are obliging the athlete to run at constant speed, whatever is the path, the profile, okay? So this is what we call natural charging. When you apply a constant voltage, the current, you cannot control the current. The current just go down, okay? So if the current goes down very fast, it means that the battery is not liking to take in a charge, okay? So this is how we connect the voltage and also the current. And then we go to the next plateau, the next voltage plateau, as soon as we see that the battery is more resilient to take a charge. So this is why NLV will be the future technology for charging batteries in the 21st century.
Yeah, so for the charging protocol, you can give a very good explanation. I'm not sure you can hear me.
Yes,
Sorry,
yes.
Professor Huang.
Yeah. So at the end,
Sorry.
that is transfer number, lithium-ion diffusivity, and material failure. So whatever this, the protocol, eventually the fundamental is lithium-ion, the transport, including the diffusion coefficient, diffusivity, and transfer number, of course, electrode structure. So the same structure, if there's a limitation that just depend on the changing the charging protocol. So that's my point.
Yes, you're absolutely right. Yes. Dr. Huang,
a challenge to do so. Yeah.
You are absolutely right. It's the kinetics, the lithium transfer, the diffusion that plays a role. So we cannot oblige lithium to diffuse. Okay, so that's it,
Yeah.
the point. The diffusion is a natural process in an anode and a cathode, depending on the again the chemistry and also the size of the particles, this kind of things. That's and the tortuosity, inside the electrode and the electrolyte and so on. So personally, when I receive a battery, it's a black box. I don't know what is the anode and the cathode. I don't open a battery, but I apply my protocol NLV. And I find that, yes, it works, whatever is the chemistry, which means that in general, when the battery manufacturer recommend charging time, we can cut this charging time by half. So this is a message to Mr. Duong Quang. Whatever the battery you are using, I can cut the charging time by half, okay?
Yeah.
Using NLV.
I believe that you all have many other things to share, but unfortunately our time frame is limited, so I will have to end the Q&A session here. If your questions haven't been answered, or if you want to continue to connect with our speaker, please contact us at secretariat@vinfutureprize.org, and we will help you to connect with our speaker later.
Thank you.
So, as we're coming to an end of today's webinar, I would like to express our sincere gratitude to our panelists, Professor Rachid Yazami, Professor Xuejie Huang, and Mr. Duong Quang Tien. Although there is a small technical issue with Professor Xuejie Huang at the first part of the webinar, but I believe that his sharing and also the wonderful presentations from Professor Rachid Yazami and Mr. Duong Quang Tien has undoubtedly enriched our understanding of the critical issue we discussed today. And we will also want to extend our heartfelt thanks to our wonderful audience. Your active participation and thoughtful questions have made this webinar truly meaningful and valuable. And please don't forget that the VinFuture Foundation is now calling nominations for the 2025 award season. The nomination portal will be open until April 17, 2025, and we encourage you to nominate groundbreaking research or innovations that have the power to change countless lives. Thank you all for joining us today. We hope to see your continued involvement in our future events. Until then, best wishes to everyone.
Thank you.
Thank you.
Thank you.